Hey guys, welcome back. We'll continue with the drag notes. So hopefully it was helpful with the notes last week. We'll do some more this week, and I have another review video where we'll look at that as well. We have a skier one here, so a little bit different. Skier mass M is skiing down a frictionless hill that makes the angle of theta with the horizontal as shown in the diagram. The skier starts from rest at times t equals 0 and is subject to velocity-dependent drag force due to air resistance that's equal to negative bv, where v is the velocity of the skier and b is a positive constant. Express all algebraic answers in terms of m, b, theta, and fundamental constants. On the dot below that represents the skier, draw a free body diagram indicating and labeling all the forces that act on the skier while the skier descends the hill. So it has mg, normal, and bv. That would be it. It wouldn't be negative bv because that negative is just telling us the direction and our arrow points in the direction, so that takes the part of that. I'll write a differential equation that can be used to solve for the velocity of the skier as a function. So I'm going to rotate my equation, and I'm going to say that f net equals mv, and I'm going to have mg sine of theta minus bv equals ma. So I have mg sine of theta minus bv equals m dv dt. I'm going to get this part to the other side, so I'm going to have dv over mg sine of theta minus bv is going to be equal to 1 over m dt. Determine an expression for the terminal velocity of the skier. That's going to be the case when f net equals 0. So that's going to be when mg sine of theta is equal to bv. And so that's going to be when mg sine of theta over b is equal to bt. So I know the integration part is laborious and has a lot of steps to it. So if you're unfamiliar with that or uncomfortable with that, all of these problems ask for terminal velocity, and they always ask for drawing graphs. So there's no reason why you can't get a good amount of points just from doing that part. All right, solve the differential equation in part B to determine the velocity of the skier as a function of time. All right, did they give us any? Starts from rest at time t equals 0. So that's it. All right, so this can go from 0 to t, and this can go from 0 to b. And when I do this, I'll be able to have a definitive integral there. All right, so I'm going to let u equal mg sine of theta minus bv. And so that's going to mean that du is going to be equal to minus b dv. And so dv would be equal to minus du over b. And so I'm going to have 1 over m from 0 to t of dt is equal to, from 0 to v, dv is negative du over b. So I'm going to put that on the outside of my integral over u. So I'm going to get t over m equals negative 1 over b natural log of u from 0 to v. So I think I'll get this over to the other side too, just to make my life easier. So I'm going to have minus btm on this side. And I'm going to have the natural log of, so I want to put back in for u my mg sine theta minus bv from 0 to v, and that's going to give me the natural log of mg sine of theta minus bv minus the natural log of mg sine of theta. And then I know that when t equals 0, v equals 0. Which works, right? Because I'm going to have the natural log of this, and that's going to be 0 when v is equal to 0. So natural log of that minus natural log of that. Okay, so that works. So I can rewrite this as then I can take both sides to the power of e, which is going to give me mg sine of theta minus bv over mg sine of theta. And so I'm going to have mg sine of theta e to the negative bt over m is equal to mg sine of theta minus bv. Why don't I add this to that side and subtract this from this side? And I'm going to have that bv is going to be equal to mg sine of theta 1 minus then I can divide by b. So I have that v of t is equal to mg sine of theta over b 1 minus e negative bt m. As this gets bigger, it's going to approach 1. So it's going to approach 0, right? And that means I have mg sine of theta over b, which should be what we got for terminal velocity. So with mg sine of theta divided by b, our terminal velocity, it was. So that works. And again, you could memorize all of the different parts and just substitute it in, and that's why they make you actually show like the steps of your differentiator. On the X below, sketch a graph of the acceleration A of the skier as a function of time and indicate the value of A. Indicate the initial value of A. Take downhill as positive. All right, so our A is going to start off being g sine of theta. And then as it develops velocity, we're going to have to subtract the portion that is accounted for the drag force. So our acceleration starts at this. Our acceleration should decrease down towards 0. So I say this is g sine of theta. Remember, our acceleration on a frictionless incline is always g sine of theta. All right, a ball of mass m is thrown vertically upward with the initial speed of v naught. It experiences a force of air resistance given by F equals negative kV, where K is a positive constant. The positive direction for all vector quantities is upward. Express all algebraic answers in terms of m, k, v naught, and fundamental constants. Does the magnitude of the acceleration of the ball increase, decrease, or remain the same as the ball moves upward? All right, so let's look at our free body diagram. As it moves upward, we have kV directed down, and we have mg directed down. As it goes up, it's going to slow. And since our acceleration is related to this velocity, our acceleration will decrease. So the acceleration is proportional to the speed. Write but do not solve a differential equation for the instantaneous speed of the ball v in terms of t as the ball moves upward. All right, so we're saying that F net equals ma, and minus kv and minus mg is equal to ma. I'm going to rewrite a as dv dt. And I'm going to get the B's and the DV's together, and I'm going to get the DT's and everything else on the other side. So I'm going to end up with dV over minus kV minus mg is equal to dt 1 over m. Why don't I multiply both sides by -1 to get this over there, because that's easier to deal with. And then we have this. Determine the terminal speed of the ball as it moves downward. So when it goes down, our air resistance is going to switch. Our terminal velocity is going to be when the force up equals the force down. Does it take longer for the ball to rise to its maximum height or fall from its maximum height down to the height for which it was thrown? All right, so thinking about this, and this is it coming down. When it is coming down, its acceleration is equal to kV minus mg over m. On the way up, its acceleration, and I'll say the magnitude of its acceleration, right, just so I don't have to worry about all the negative stuff, is equal to kV plus mg divided by m. What else do I know? The distance is the same. And I know that the one is going to end at 0 and the other one starts at 0. So that relates the two velocities. So if I have the same distance and I have less acceleration, it's going to take more time. So it's going to be longer to fall. We could justify it with how our acceleration is. We could also justify it in terms of conservation of mechanical energy. If you think about it, it starts with a certain amount of mechanical energy. Then mechanical energy is shrinking as it goes up and then shrinking as it comes back down, right? Because we are losing energy to that non-conservative force. That's what air resistance is. And so it's going to end up with less kinetic energy when it gets back down, though, than it must have taken a longer amount of time to go the same distance. On a axis below, sketch a graph versus time for the upward and downward parts of the ball's flight, where TF is the time in which the ball returns to the height from which it was thrown. So it's going to go the whole thing, and we have a graph that has a split in the middle. So I want this to curve down, and I want my second part to take longer than the first. I want this magnitude to be bigger than that magnitude, because it's not going to reach the same velocity that it did. So the two important parts is that this is less time and this is less speed.